Hello, today we're going to talk about section 2.7, which is on VSEPR, which stands for valence shell electron pair repulsion, and hybridization. So all about molecule shapes and why they have their different shapes, and then how the orbitals can hybridize in molecules up to tetrahedral. So VSEPR stands for valence shell electron pair repulsion. You can break that down into a couple of statements there. Valence shell, so the outermost, electron pairs repel each other. Right, so it's VSEPR theory. So what that means is if you have, let's say we have formaldehyde. Around that carbon, that central carbon atom, there are three areas of electrons. We have a single bond, and a double bond. So there's three areas of electrons around that carbon. Because of VSEPR theory, valence shell electrons, they repel each other. So those three areas of bonding are going to spread out as far as they possibly can because the electrons in those bonds are repelling each other. And that's kind of the whole point of VSEPR. And it winds up creating a certain predictable structures for the molecules for us to look at. Okay, so let's look at the first sets of structures. Now, if you only have two areas of bonding, or areas of electrons really, around a central atom, it must be linear. Okay, so in this diagram it says number of charge clouds. We also call those electron domains. Electron domains, just areas of electrons. And if there's only two areas of electrons around a central atom, like the two here, then it's linear. They have to spread out evenly. Now, if you have three electron domains, those three are going to spread out completely evenly around the central atom, just like formaldehyde that we were looking at on the previous slide. They drew it kind of in 3D space here, but if I draw it flat, it would look like this with this oxygens, the two hydrogens. It spreads out evenly. That's called trigonal planar. All right. What happens though sometimes is we have things that will have a lone pair on the central atom. So if one of those areas of electrons is actually a lone pair, then we call it bent. It still has trigonal planar electron domain geometry because it has three areas of electrons. We just distinguish that one of them is a lone pair by calling it bent. Now, since we're talking about it, let's also talk about bond angle. So the angle between these two bonds in a linear molecule must be 180 degrees because it's a straight line. But if it's trigonal planar, then you're going to have, roughly 120. Because imagine a circle is 360 degrees divided by the three areas of bonding, so that's going to be a 120 degree angle. If one of those winds up being a lone pair instead, like that, the lone pair exhibits just a little bit extra repulsion than a bond does. So it would be just a little bit less than 120. So you could say it's like 117, 118, something like that. You don't need to know an exact number, just a little less than 120. So that's for three electron domains. If you have four electron domains, now you have to start thinking in three dimensions. 4 electron domains would wind up being tetrahedral. Okay. Imagine a tripod with something sticking out the top. Okay. So a tetrahedral, the angle there is very specifically 109.5. And you do need to know that number, 109.5, because it's in 3 dimensions. So each of those bond angles is identical around the central atom in 3D space. And again, if one of those atoms were replaced with a lone pair instead, it would still be called tetrahedral electron domains because it still has 4 areas of electrons, but you distinguish the molecular geometry. So if one of them was turned into a lone pair, it would be trigonal pyramidal instead. like ammonia. And if you have 2 lone pairs instead of 2 atoms, then it would be bent. But like I said, both of these, even though they're trigonal, pyramidal, and bent, they still have tetrahedral electron geometry. Now we also have 5 electron domains and 6 electron domains. If there are 5 electron domains, the base structure would be trigonal bipyramidal. And these other ones are also considered trigonal bipyramidal in terms of their electrons. But they have different names based on the number of lone pairs. So if there's 1 lone pair, we call that a seesaw. If there's 2 lone pairs, it's T-shaped. And if there's 3 lone pairs, it's down to linear. And then when there's 6 electron domains, we call that octahedral, and that's the base structure, octahedral. The other ones are also octahedral in terms of their electrons, but if you have 1 lone pair, we specify that it's square pyramidal. If there's 2 lone pairs, it's square planar. If there's 3 lone pairs, it would be T-shaped, and 4 lone pairs would be linear, but those don't come up very often. Now, in terms of bond angles for these ones, it gets a little more complicated because it depends on which atoms you're referring to. So here's a nice little summary of all of that information. This refers to the number of electron domains. This is the name of that electron domain geometry. So it doesn't get specific with like bent or trigonal planar or any of that stuff. But it does tell you the shape of the electron clouds. And it tells you the angle, okay? And that is the base angle, right? So linear is always 180, trigonal planar is 120. If one of them is a lone pair, it's going to be slightly less than 120. Tetrahedral is 109.5, and if you add lone pairs, it will be slightly less than 109.5. Generally, we say like 107, and then if there's 2 lone pairs, it's 104. Trigonal bipyramidal, it's 90 and 120, depending on if you're talking about atoms that are at a right angle to each other versus atoms that are in the triangle around the center. And then the last one, octahedral, is typically 90 degrees. Now, the last column here is for hybridization. This is talking about which orbitals are involved with making the bonds around that central atom. So if you have something that's linear, we're just going to call that SP. The way I like to think of it is that linear has 2 areas of bonding around the central atom. So 2 things, we have SP, that's also 2 things. It's a good way to remember it. With trigonal planar, you have 3 electron domains, 3 areas around the central atom. So we say it's SP2. So imagine there's 2 P's there. S and 2 P's, that's 3 things. So SP2. Trigonal planar has 4 areas of bonding. So 4 areas of bonding. You're going to have 4 orbitals involved, S and 3 P's, or SP3. Trigonal bipyramidal has 5 electron domains. So we'll have 5 orbitals. But at this point, we've run out of p orbitals. You can never have more than 3 p orbitals in a sublevel. So now we have to add a d in. So S, 3 p's, and a d. Notice how there's 5 letters for the 5 electron domains. And the last one, 6 electron domains, 6 orbitals, sp3d2. So let's talk about sigma and pi bonds. Sigma bonds, which has this symbol, sigma bonds, result from the end-to-end overlap of orbitals. So if you have an overlap of s orbitals, an s with a p orbital, or the ends of 2 p orbitals like this, where you have just one overlap, that's called a sigma bond. And remember, the orbitals have to overlap so the electrons can be shared and a covalent bond can be formed. For a pi bond, you have to have these p orbitals overlapping lengthwise, basically, side-to-side overlap. And you wind up with multiple overlaps like this, which makes it a shorter and stronger bond. So this happens when you have double or triple bonds. when you're counting sigma bonds, you want to count each bond having at least one sigma bond. So you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 sigma bonds in that giant molecule there, because you count every single bond once. For pi bonds, you'll count the double and triple bond. Each is 1. So you'll do, there's 1 pi bond there, and there are 2 pi bonds in the triple bond. So in this molecule, there are 3 pi bonds total.